let us discuss another question from the chapter on alternating currents. When an EMF E is equal to E naught sine 100t is connected across a circuit, the current I leads the EMF E by pi by 4. If the circuit consists of only RC or maybe only RL in series, find the possible combination of the two elements, and various combinations of R and C in the first two options and combinations of R and L in the second, third and the fourth options are given. Now first we will look at the question and understand and extract a few pieces of information. First thing, EMF E is equal to E naught sine 100t. From this, one piece of information that we will take is that the value of omega. The value of omega is 100 because we know E is equal to E naught sine omega t. Here we have 100 in place of omega, so the first thing that we will take down is omega is equal to 100 radians per second. Next, very important piece of information for this question is the current I leads the EMF by pi by 4. The very important point is I leads E. So the current leads the EMF by pi by 4, and we know that it is in a capacitor that current leads the EMF by pi by 4. We know that if it is a purely capacitive circuit, if an AC source is connected to a purely capacitive circuit, then of course the current will lead the EMF by pi by 2. But if it is connected in series with a resistor, then it won't lead the EMF by pi by 2, but by a lesser phase angle. So here this statement, the current I leads the EMF by pi by 4, is very clearly telling us that our circuit is not going to contain RL, but it is going to contain only RC. Therefore, only RC components we are going to conduct, and RL is not going to be there. Because if we had RL, then voltage would have been leading the current. Here the current is leading the voltage, therefore definitely the circuit is going to be an RC circuit, because they have clearly told that we need not consider a LCR circuit because the combination could be either RC or RL. So children, now the question is find the possible combination of the two elements. Now what is that we need to do? The first thing that we can do is that we will use this second piece of information, which is pi by 4. Pi by 4 is the angle by which the I leads the EMF. Therefore, we have learnt that tan phi is equal to XL minus XC by R if the circuit is inductive, XC minus XL by R if it is capacitive, in case if it is an LCR circuit. But here what we are talking about is only an RC circuit, therefore there is no question of XL coming into picture. Therefore tan phi will simply be equal to XC divided by R. So tan phi is equal to XC divided by R. Now here, one more thing at this point, what we can finalize is option C and option D cannot be our answer because they are R and L. We have already decided, or we have already concluded, that our circuit is going to be a combination of R and C only because current leads the EMF. So now we know that XC is equal to 1 by C omega. XC is equal to 1 by C omega. Therefore, we will substitute this in this place. So tan phi will become equal to 1 upon C omega divided by R. So if I write this as 1 by C omega into R by 1. So here it is R by 1. So this, if I bring it to the top, it is 1 by R. So therefore we get tan phi is equal to 1 by C omega R. Now here children, phi value is pi by 4. So therefore tan pi by 4 will be equal to 1 by C omega R, tan pi by 4 will be equal to 1 by C omega R. Now, because tan pi by 4 is 1 by C omega R, and we know that the tan value for pi by 4 radians is 1. Tan 45 degrees is 1, or tan pi by 4 radians is 1. Therefore, 1 by C omega R is going to be 1. Therefore, if I bring R and C to the side, I will have RC equal to 1 divided by omega, because here I have 1 here, R and C I bring it here. So, 1 by omega is equal to RC. But we have already taken down the value of omega. Omega is 100 radians per second. So, therefore, this will be RC will be equal to 1 by 100. And as you know, RC is the time constant. So, therefore, the unit will be second inverse. Now, here all that is important is that R into C is 1 by 100. This is the equation which is going to be important for us to solve the question further. Now, here the question is, find the possible combination of the two elements. So, now we have a tie between A and B. We have to check whether A is the right option or B is the right option, because C and D are already eliminated because they are R and L combination. We know that it is R and C combination, that's what we are looking for. And from this equation, we can substitute the options and check which of the options is going to match this condition. RC is equal to 1 by 100. Now, R value is 1 kilo ohm. Let us substitute. Let's check the first option. Checking the first option. R is 1 kilo ohm. 1 kilo ohm is nothing but 10 to the power 3 ohms. Then multiplied by C is 10 microfarad. 10 into micro is 10 power minus 6. So, we have done R into C. So, now if you observe here, 10 power 3 into 10 is 10 power 4. 10 power 4 into 10 power minus 6 is in fact 10 power minus 2. Or you may just add the powers. 3 plus 1, 4. 4 minus 6 minus 2. Therefore, 10 power minus 2. 10 power minus 2 is nothing but 1 divided by 100. So, therefore, from the options, if we multiply R and C, we are getting 1 by 100, which is satisfying this equation. Therefore, A is the right answer. Now, if you observe B, you can eliminate that by trying to substitute it in the option. 1 kilo ohm, 10 power 3. 1 microfarad, 10 power minus 6. So, 10 power 3 into 10 power minus 6, which is 10 power minus 3. 10 power minus 3 is 1 by 1000. Therefore, if you take the second option and multiply R and C, you are going to get 1 by 1000, which is not matching with the needed equation. Therefore, the only correct answer is A, option A. So, I repeat once again, students, in this particular question, omega value is 100, I leads the EMF by pi by 4, therefore, it has capacitor. The circuit is going to contain only RC or only RL, that is the question. So, therefore, there is no chance it can contain RL because the voltage is not leading the current is leading the voltage, therefore, only RC is possible. And then we use another formula, which is tan phi is equal to XC by R. XC is 1 by C omega, 1 by C omega R is tan phi, but phi is nothing but the phase angle between current and voltage, which is pi by 4. So, tan pi by 4 is 1 by C omega R, tan pi by 4 is 1. Therefore, if I take RC on one side, RC is equal to 1 by omega, omega value is 100, we substitute here. So, RC has to be 1 by 100, and only when we substitute for R and C in this equation from the first option, it satisfies. Therefore, the correct answer is first option. Dear students, let us look at the next question from this particular chapter on alternating currents. In the given circuit, find the ratio of I1 to I2, where I1 is the initial current at t equal to 0 and I2 is the steady state current, that is at t is equal to infinity through the battery. Now, we need to understand something about inductor. Now, when we close the circuit, that means we close the switch, current starts to flow through the circuit. But inductor, as we know, has something called as self-inductance. What is that property? The property is that when current is trying to rise in the inductor, it will oppose. Because as the current is rising, the magnetic field is increasing. As you all know, students, the current flowing through a conductor has magnetic field around it. So, as the current is trying to increase, the magnetic field is trying to increase, which means the magnetic flux which is linked with the coil of the inductor is trying to change, trying to increase. And according to electromagnetic induction law, we know that whenever there is a change in the magnetic flux, there is an EMF which is induced. According to Lenz's law, it is going to be in the opposite direction. It will oppose the cause. Therefore, inductor will oppose the change in the current, whether it is rising or whether it is falling. Therefore, whether we close the circuit, whether we make the circuit or break the circuit, inductor is going to resist both of them. Inductor is going to oppose the change in current. So, this is the concept we are going to use here. Or in other words, in simple words, the current in an inductor cannot change instantaneously. Instantly it cannot change. It takes time for the current in an inductor to grow or to decay. So now this question is a simple application question based on this concept. So we understand that before we close the switch, the current through the inductor is 0. So initial current through the inductor is 0 at t equal to 0. Now, when I close the switch at t equal to 0, the current is trying to rise. The battery is going to supply the charges, but inductor will resist the change in the current. Therefore, even after the switch is closed, the inductor current is not going to change. So we can write the current through the inductor at t equal to 0 minus is equal to current through the inductor at t is equal to 0 plus. When I say t equal to 0 minus, that means I am talking about just an instant before t equal to 0. The current through the inductor at that time was 0. The moment I close the circuit, even after this time, even after t is equal to 0, that means little after t equal to 0, the current through the inductor is not going to change. That means it is still going to remain 0. So therefore, the initial current through the battery, if we have to calculate, we should understand that the current through the inductor stays what it was before. So therefore, the current through the inductor in the initial state is going to be 0. So therefore, there is no current flowing through the inductor, which means it is going to act like an open circuit. So this is equivalent to inductor not being present, which means there is no current which is flowing through this path. That means all the current that is coming here, I, is going to flow through this 4 ohm resistance, and this path is an open circuit initially. Therefore, the circuit simplifies to what I am going to draw now. So initially, at t is equal to 0, the circuit can be redrawn like this. So this is 10 volts, then we have a resistor here which is 6 ohms, and then another resistor which is 4 ohms. That's all, because this portion is going to be open circuit, since the inductor cannot change its initial current. Therefore, this path is open circuit. Therefore, there is no current flowing through this. Whatever was originally there, same thing is going to be there. So IL was 0 before, now also it will be 0. For all purpose, practical purpose, you can consider this as an open circuit because current is not flowing. Now, so all the current I that is coming here will flow through this 4 ohms itself. Therefore, the current that is going to flow in this case, which we call as I1, is going to be equal to the voltage, which is 10, divided by the total resistance, which is 6 ohms and 4 ohms are in series because there is no current through this circuit. So 6 plus 4, 10. So 10 divided by 10. So the current flowing through this circuit is 1 ampere. That is the current in the initial state. Now let us go to the next part of the question, which is steady state current. When I say steady state, that means time has passed. As the time has passed, the current, as we know in an inductor, grows, and after time t is equal to infinity, which means the current has reached its maximum value, then inductor will behave like a short circuit. Then inductor will not oppose any change in current, because there is no change in current, because the current has reached the maximum value. So current is not changing now because it reached maximum value. Therefore, the magnetic field and the related flux through this particular coil is not changing. Therefore, inductor does not have any opposition, and as we know in a DC circuit, the omega value is 0, therefore XL is 0 anyways. Therefore, inductance, you can replace this with a short circuit in the second case. That means in the steady state, if you want to redraw the diagram here, it will be, we have the 6 ohm here, we have the 4 ohm here, and this 2 millihenry inductor can be replaced by a short circuit in the steady state. Therefore, this will be the circuit that we have to analyze now. This is 10 volts and this is 6 ohms, and here we have 4 ohms and here we have another 4 ohms. So this becomes quite a simple electric circuit problem to find the current, and the current supplied by the battery is I2 in this case, the steady state. Now how do we do it? Very simple. 4 ohms and 4 ohms are in parallel, therefore the effective resistance is 2 ohms. Students, you can remember that if a resistance R and another resistance R are in parallel, that means two equal resistances R and R are in parallel, then the effective resistance will be R by 2. Suppose three resistors are in parallel, then the effective resistance will be R by 3. So here children, 4 ohms and 4 ohms are in parallel, therefore the effective combination of these two is 2 ohms. And that 2 ohm resistor is in series with 6 ohm resistor. Therefore the total resistance is 8 ohms. So therefore the current here in this case is going to be the total voltage, which is 10 volts, divided by the total resistance, which is 2 ohms plus 6 ohms, which is 8 ohms. 10 divided by 8 ampere is going to be I2. Now I will tell you, for a reason we need not simplify this, because we are not asked I1 or I2 separately, we are asked to find the ratio. So last step of this particular problem, we need to find I1 by I2. I1 by I2 is equal to 1 ampere divided by 10 divided by 8. So this 8 in the denominator of the denominator comes to the numerator. 8 by 10 is 0.8. Therefore, the required ratio for us in this problem is 0.8, which is the second option. Now to summarize, couple of concepts that we need to remember is that in initial state, the current through the inductor is 0. That means this you can replace with an open circuit. And then the solving becomes very simple. In that case, I1 is 1 ampere. The second part of the problem, in steady state, the inductor can be replaced by a short circuit. Then we simplify this equation, we get the current as 10 by 8 ampere. Therefore, the ratio is going to be 1 divided by 10 by 8, which is 8 by 10, which is 0.8. Now let us analyze the statements one by one. Statement number 1, it says that the rate of change of current with respect to time at a particular instant is 8 ampere per second. And we know that rate of change of current with respect to time is di by dt. Therefore, di by dt is equal to 8 ampere per second. Now we know that there is a relationship between E and di by dt. The voltage across the inductor VL is equal to L into di by dt. Now here, if we observe here, we need to find the voltage across the inductor. The voltage across the resistor is 4 volts. Therefore, the resistance is 4 ohms and the voltage across the resistor is 4 volts. Now, if you see, the total voltage is 20 volts. So, total voltage being 20 volts, that voltage will be equal to, the total voltage 20 volts will be equal to VR plus VL, the voltage across the resistor plus the voltage across the inductor. Now, the voltage across the resistor is given in the question, which is 4. So, therefore, VL value becomes 20 minus 4, which is 16. So, this implies VL is equal to 16 volts. So, therefore, the voltage across the inductor is 16 volts. Now, if you compare in this equation VL, we can substitute as 16. So, this implies 16 is equal to L into di by dt. But L value is given in the question as 2 Henry. So, therefore, instead of L, we can substitute 2 Henry into di by dt. So, di by dt becomes, di by dt will be equal to 16 divided by 2, which is equal to 8. Therefore, 8 ampere per second, which is 16 by 2, is correct. So, we observe that this statement which says di by dt is equal to 8 ampere per second is in fact correct. So, statement 1 is definitely true. But however, to get the final option, we need to analyze all the other statements also. Now, let us look at the statement 2 now. Statement 2 is that power provided by the battery is 20 watt. Now, how do we find the power provided by the battery? We know the formula that power is equal to voltage into current. For this, we need to find the value of the current flowing through the circuit at that instant. Now, we are given the information that VR, the voltage across the resistor, is 4 volts and the resistance is 4 ohms. So, we know from Ohm's law V by R is I. Therefore, 4 volts divided by 4 ohms is the current. So, the current is 1 ampere. So, the current value is 1 ampere. The voltage of the battery is 20 volts. So, if we multiply these two, 20 volts into 1 ampere will be equal to 20 watt. So, therefore, the power provided by the battery is 20 watt, which is also correct. So, therefore, the statement 2 is correct. Now, let us go to statement 3. Statement 3 is the power stored in the inductor is 16 watt. Now, we know that the total power is nothing but the power dissipated in the resistor plus the power stored in the inductor. Now, the power which is going to be stored in the inductor is going to be, let us find, which will be PL is equal to P minus PR. Now, we already got the value for P. The value of P is 20 watt. So, we substitute 20 here. Then, the power that is going to be dissipated in the resistor is given by the formula I square into R. Therefore, we see that I square, I is nothing but V by R, which is 4 by 4, which is 1. So, I is equal to VR by R, which is 4 divided by 4. So, it is equal to 1 ampere. Therefore, we see that for the current I, we substitute 1. So, 1 square into resistance is 4 ohms plus PL. So, thereby we get 20 is equal to 4 plus, or in other words, PL is equal to 20 minus 4, which is 16 watt. So, therefore, we can see that the statement 3 is also correct. So far we have seen statement 1 is correct, statement 2 is correct, statement 3 is also correct, and we have already found that the statement 4 is correct because I value we already got it as 1 ampere. Therefore, statement 4 is also correct. Therefore, the correct answer for this question is all the 4 statements are correct, which is nothing but the 4th option. Therefore, the right answer for this question is option D. Dear students, I hope in today's class you have learnt the basic concepts in alternating currents and the different types of questions that can be asked in the CET examination. And in fact, as you would know, there are about 3 to 4 questions which come from this chapter in the CET examination, and I wish you all the very best for the coming CET examination and all the best for your future endeavors.